I'm Mike Morris. I'm with Ocean Optics, and today I just want to show you how our modular spectrometer is now being used to analyze dirt. And dirt's pretty important because dirt feeds animals, dirt feeds us. What we came up with is a way to look at the near-infrared reflection spectroscopy of dirt. And in the dirt, you can find urea, which is a source of nitrogen for the plants. You can find moisture, and you can look at the organic matter in the soil. And so better management of your farm comes from a sensor that can tell you where those things are abundant, where they're missing. So then we look at the soil itself. So being a chemist, I grew up in the age of test tubes and solutions are nice because everything is the same all throughout that sample. That's not true of dirt. You look at dirt, it's a bunch of things. Rocks, pebbles, it's inconsistent. And so to get around the problem of consistency, we came up with a really elegant but very simple solution. And that is, we just look at a lot of different locations in the dirt and average it out. So now we're going around a circle, we're taking 20 spectra, averaging them, and now we're getting a good average of that sample of soil. So here you have it, a very small, compact spectrometer. Easily field portable, can be put on a tractor, we can put fiber optics wherever you want them, pointing at whatever you want to see, and now we have the perfect solution for analyzing dirt on a very big scale.
Thank you, Mike, for that great introduction to this demonstration that we're showing here and how we can use modular spectroscopy in a precision agriculture application. For these measurements, we're using our NIRQuest 512 1.7 spectrometer, which is looking at NIR wavelengths from 900 to 1700 nanometers. We're also using our Rotocup sampling accessory, which, as Mike described, enables to get a very representative sample of these real-world heterogeneous samples that we find on a farm. We're using OceanView to acquire our spectral data. So you can see right now we're seeing a spectrum for some soil from a cornfield. And then we're doing predictions in real time of the moisture, urea, and organic content for these samples. We're measuring 20 spectra as this rotates, and we're getting a nice, stable spectrum. To give you an example of how important this representative sampling is, if I decrease my number of averages, so we're looking at a single point on the sample, we then will begin to see a lot of variability in our sample. And so we won't know what the actual values are for the moisture, urea, and organic content. Now it's important to note that these variations that we're seeing when we're only looking at a single point are not related to the equipment itself or to the spectrometer or the measurements. They're actually related to the inhomogeneity of this sample. As you can see, there are differences in the height of the sample. You can see there are differences throughout. And these results, although accurate, are not as valuable and representative to help the farmer make sure that he's treating his soil appropriately to maximize his yields and minimize waste. To learn more about this and other applications of spectroscopy, see us online at oceanoptics.com.